So first we have Dr. Sanjukta Roy of RRI. Presently she's at RRI. And she is, of course, her credentials are really fantastic. I mean, she's Unni student, or we know Unni for a very long time, Professor Unni Krishnan student of TIFR. She was involved in the, the BEC work that they were doing those days. It was fantastic. The first time that BEC had been done. After that, a postdoc is with Nobel laureate, Cohen Tanuji. I'm sure everybody here has at least once looked at Cohen Tanuji's quantum mechanics books, followed it up with another, postdoc with in Florence with Professor Ingusio, whose papers I used to follow when I was doing my PhD. And now, of course, she's at RRI, and her research interests are, the Rydberg atoms is something that is extremely, extremely in these days, for lots of nice applications. But along with that, she's also doing, along with Rydberg atoms, few body physics, Anderson localization of matter waves, disordered potentials. But I think I'm most, really interested about what she's doing with Rydberg atoms. So, Sanjukta, it's yours.
Thanks for the kind introduction. And I thank the organizers for inviting me to this fantastic discussion meeting on structured light and spin orbit photonics, especially because the future direction of cold Rydberg atoms in our experiment is heavily based on cold atoms in structured light potentials, so which is the future of our experiment. So this is very relevant to this meeting.
I'll give you a warning at 5 minutes left.
Sure. Sure. So today I'll be talking about quantum interference with cold Rydberg atoms. So the outline of my talk is, first I'll give you an introduction to the exotic properties of Rydberg atoms. And then I'll talk about our recent measurement results on very high precision measurement of transition frequencies of highly excited Rydberg states. Then I'll talk about our ongoing measurements on quantum sensing with Rydberg atoms. And I'll talk about our recent observation of Rydberg excitation in cold atoms, which opens up a lot of possibilities on quantum technology with ultra cold Rydberg atoms.
I have a request.
Yeah.
Your mouse, that cursor.
Yeah. Yeah.
Floating around. Point it to the board when you are not pointing.
Sure. Sure.
Your pointer, yeah.
So then I'll talk about measurement of the second order correlation function in cold Rydberg atoms, which is also ongoing. And then I'll talk about our future directions on trapping of single atoms in optical tweezers and exciting them to highly excited Rydberg states. And then I'll give you a future perspective on quantum information with arrays of single Rydberg atoms in structured light potentials. So Rydberg atoms are giants of the atomic world. So Rydberg atoms are atoms where the electron is at very, very high principal quantum number, very far away from the nucleus, making it a giant superatom which has many exotic properties, and which makes it a very useful candidate for many applications, including looking at many body physics and quantum technologies. So Rydberg atoms was discovered by Swedish physicist Jonas Rydberg in 1988. He found an empirical formula which linking the various wavelengths of the spectral lines observed in alkali atoms, which was used in the famous Bohr's paper in 1913 on spectra of atoms. Sorry, this is typos, 1888. So the energy of the atoms in the Rydberg state is given by this expression, where EI is the ionization energy, and Ry is the Rydberg constant, and delta is the quantum defect. So in Rydberg atoms, since the electron is very, very far away from the nucleus, it's essentially like a hydrogen-like atoms because the inner electrons are screening the charge of the nucleus. So the outer electrons is essentially like a hydrogen-like atom. But what happens is for atoms, for orbitals with low angular momentum, the orbitals are actually penetrating into the electronic core. So the electron does not have, it sees the screening of the inner, screening of the charge as seen by the electron is not complete. So that's why this quantum defect has to be introduced, which makes this correction for lower orbitals, which has incomplete screening of the inner electronic core. And so Rydberg atoms being so large, it had a very important role in the birth of quantum mechanics in the early days. So as I was saying, atoms in the Rydberg state, they acquire some exaggerated properties because of the fact that the electron is very, very far away from the nucleus. So the energy of the Rydberg state, it goes as 1 by n to the power square. The energy level spacing goes as 1 by n to the power cube. And then, very interesting, the radius of the Rydberg atoms goes as n to the power square. So that means for very high principal quantum number, they are giant atoms which are ideal for exploring mesoscopic quantum regime, which I'll describe in the later part of my talk. So just to give you a comparison, for a ground state atoms which are generally of the size of angstrom, a Rydberg atom can be of the size of a micron, like the size of a human hair. So which is like really into much, much larger than ordinary ground state atoms. Also, the lifetime of the Rydberg atoms is very large, which goes as n to the power cube. That means it gives long coherence time for quantum technology applications. Also, the polarizability, which is very important, which makes the Rydberg atoms very important as a quantum sensor, goes as n to the power 7. That means it's extremely sensitive to small DC or AC electric field. That means it's very important for quantum sensing and metrology. Also, the resonant dipole-dipole interaction coefficient, it goes as n to the power 4, and the van der Waals interaction coefficient goes as n to the power 11. So these very large interaction between Rydberg atoms and also long range makes it very desirable for having quantum entanglement via Rydberg blockade. I'll be describing in a few slides, which enables realization of fast quantum gates for quantum computation. Also, we can do quantum simulation of many body physics in quantum condensed matter systems. And also, Rydberg atoms can be used as single photon source due to the strongly interacting nature and can be used for quantum communications. So why cold Rydberg atoms is so interesting? Because cold atom systems are highly coherent system because of the ultra cold temperatures, and the quantum regime becomes accessible at very, very low temperatures because the de Broglie wavelength goes as inversely proportional to the square root of temperature. So colder we get, larger is the de Broglie wavelength, and we go more and more towards the quantum regime. And we have a high degree of controllability at very fast time scales. We can switch the interaction within a fraction of a microseconds. And there's a strong coupling to light with negligible Doppler shifts. And we have complete control of interatomic interaction. That means we can excite to the Rydberg state and have long-range dipole-dipole interaction just by switching on the laser, which is giving rise to the Rydberg excitation. That means we can have very fast control of the interatomic interaction. And of course, we can control the temperature, the dimensionality, the atomic spin states to a high degree and that makes it an extremely highly controllable system for quantum processing. So the very interesting phenomena which makes Rydberg atoms very suitable for realizing quantum entanglement and quantum gates is what is called a Rydberg blockade. Now, the Rydberg atoms, which I mentioned before, has a very, very high, values of interparticle interaction. For example, the van der Waals interaction goes as n to the power 11, which is like 14 orders of magnitude more for, say, n equal to 100 as compared to ground state atoms. So if the two Rydberg atoms are very far apart, then we don't have any interaction. But as the Rydberg atoms are coming closer, then because of this interaction between the atoms, the energy level of the other atom gets shifted because of this interaction. And so the laser, which is exciting to the Rydberg state for one atom, it cannot, because of this energy shift, it's off resonant with the other atomic transition, so it cannot excite the other atom to the Rydberg state, and vice versa. So if you can excite one atom to the Rydberg state, you cannot excite the other, and vice versa. So you can see that there's a correlation which is formed because of this what is called a Rydberg blockade, and because of this correlation, we can form an entangled state. So this forms the basis of creating quantum gates with Rydberg atoms. To give you the typical numbers for n equal to 7200, the blockade radius, that means the characteristic range of interaction of the Rydberg atoms is around 10 microns. So it's pretty long range interaction. So the importance of quantum entanglement was recognized very recently by the Nobel Prize in Physics in 2022, which was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So this is the big photograph of our Rydberg experiment. So this is the Rydberg experiment team. So Shilpa, who is here, who is also presenting a poster outside. She is the PhD student, along with Shobhan, who is also a PhD student, and Venkat and Abhay are visiting students in our lab. Yeah, so this is the laser at 480 nanometer. So this is what is called a TA-SHG Pro frequency doubled laser. So it has the master laser at 960, and then there's a bow tie cavity which does a frequency doubling at 480 nanometer, giving a very nice, beautiful blue laser. So we detect Rydberg atoms using what is called a Rydberg electromagnetically induced transparency, which is a very accurate and efficient as well as non-destructive detection for Rydberg atoms, for atoms in the Rydberg state. So electromagnetically induced transparency is a very interesting phenomena. So it's actually it's a very interesting quantum interference phenomena. So electromagnetically induced transparency can be observed in various kind of system. For example, a V type of system where you have one ground state, two excited state, or a lambda kind of system where you have one excited state and two ground state, and also a ladder type of system which we are using here where you have two transition one after another. So here what we are using as in an electromagnetically induced transparency, suppose you have just a two-level system and you are probing the two-level using a probe laser. So when the probe laser is tuned to the resonant frequency, you get absorption. But when you have a three-level system and you have another transition which is addressed by what is called a coupling laser, because of the destructive quantum interference of the transition probabilities of this two transition, it leads to a cancellation of absorption and you get a maxima of transmission, a complete cancellation of absorption, which is the electromagnetically induced transparency. So it's a beautiful quantum interference phenomena which also is very useful for detection of Rydberg atoms. So here is our Rydberg EIT signals. So this is basically this transmission peak inverted and the background is subtracted. So it gives you a nice signal with a flat background. So this is what we had used for detecting the Rydberg atoms in the first place.
How did you create the Rydberg atoms?
So this is what I said. We are actually creating using this two-photon transition.
That itself is enough.
Yes, that itself is enough for creating the Rydberg atoms as well as detecting it, because we get the
Scheme is ladder scheme.
ladder scheme. Yes.
I mean, is the efficiency not less? I mean, just is this good enough?
Yeah, we have a very good efficiency. You can see from the signal we get.
Transmission you are plotting, right?
Yeah, this is the transmission we are plotting. So when we started this Rydberg experiment, so we had set it up just before the pandemic, and after the pandemic in the beginning of last year, we wanted to go to very high Rydberg states. Now, we didn't have the transition frequencies anywhere in the literature where we could just tune our laser and excite it to the Rydberg state.
Theoretical query.
Yeah.
How far can you go? How large can you make this?
Yeah, so we can go as large as possible, depends on how good signal to noise.
What limits your?
So we have gone to 125 till now, depending on our present detection system. So of course we are improving our detection system to have much higher signal to noise ratio so that we can go to even higher Rydberg states. So this, as I will explain,
Lack of your detection system.
so it's just that
Sensitivity is less, right?
yeah, sensitivity, because when, as I will explain, when we are going to higher and higher, say beyond 125, so the Rydberg EIT signal, even after lock-in detection, it had less signal to noise ratio. So we were not completely, we wanted to be completely sure of our accuracy of our.
The probability of generating such high states is very small. So
Yeah, it's of course goes as 1 to the power n cube. Sorry, 1 by n cube. So it's as you go to higher and higher states, the transition probability also reduces. So the best way we thought to go to know these frequencies to go to higher, very highly excited Rydberg states is we thought to measure it ourselves. So we made a very precise measurement of the transition frequencies of this highly excited Rydberg states from n equal to 45 to all the way to 125. So till then, in the literature, the available transition frequencies were only till n equal to 50. So we went all the way to 125 and made accurate measurement of this transition frequencies. Well, most of the measurements had an accuracy of 1 megahertz, but we are conservatively quoting as 2 megahertz. So we could measure all the way the transition frequencies to 125. And so here, in the next slide, so this is the fine. Yeah. Which one? Yeah. Oh, yeah. So this is one signal which we are, fixing in the frequency, and then we are demonstrating that as we are going to higher and higher Rydberg state, the fine structure splitting is becoming smaller and smaller.
that's like a control.
Yes, that's like a control. So that's what we are showing here, that the fine structure. Yeah, we can continuously. So as I was saying, it's a frequency doubled laser. So what we do is we measure, we tune the frequency of the master laser. So automatically the frequency doubled laser frequency is also changing, which we can tune to different Rydberg states.
As you go from lower end to higher end, your frequency remains intact or changes?
No, yeah, excitation frequency changes. It becomes higher and higher. So we go to higher and higher frequencies to address, lower Rydberg states to higher Rydberg states. Yeah. So we get in a range of 480. Now the frequency double laser has a tunability all the way from 474 nanometer to 483 nanometer. So in this,
much lesser than that.
yeah, it is much less than that. Yeah, it's around 480 nanometer. Yes. Yeah, it's very highly tunable, that laser. So here it's just a subset of a whole lot of measurements. where we are showing the signals from, all the way the Rydberg state from n equal to 45 to n equal to 125. So here we have the dots, which are a lot of them in number. So these are the experimental data points, and we have fitted them with the theoretical expression to get what is called the quantum defect, which I had mentioned in the beginning of the talk. So this we could get to a very high accuracy of 1 megahertz, and we could also get the ionization frequency of the Rydberg state from these measurements, which was recently published.
And is it possible to also know about the Rydberg blockade radius in all these calculations?
Yeah. So that's why cold atoms are so interesting, because in the cold atoms we can, it's highly.
I'm saying current data.
Current data we have to, look at a bit higher density. So in room temperature atoms, the densities are not so much as cold atoms. But nowadays people are making micrometer cells where that limitation is overcome by having very high density even in room temperature atoms. So there we can probe Rydberg blockade. So here, this is also an ongoing experiment where we are doing an experiment towards quantum sensing with Rydberg atoms. As I mentioned, Rydberg atoms being highly sensitive to electric and magnetic fields. So here we have used, instead of one coupling beam, which was just co-propagating in the earlier case, we are using a standing wave configuration. And here we see something and also we are applying a magnetic field using a solenoid. And here we see, instead of one EIT, we see two peaks. One is from the counter propagating, which is the usual EIT signal, and also another one from the co-propagating, because of the co-propagating coupling beam. So as here what we are doing is we are changing the frequency of the coupling beam, and we see here the relative positions of the two.
Has it got anything to do with the normal mode splitting or something? You are coupling the cavity mode. You have this counter-propagating thing.
Yeah.
Because you have a cavity mode, right?
So yeah, no, I mean we are not using any cavity with the atoms. It's just the two peaks.
This is like a SAT-APS kind of thing.
Yeah, more or less.
The same or
Yeah, the powers are same. Yes. So here you can see the different ZMan states of the Rydberg atoms. So what we have done is to do a ZMan spectroscopy of the Rydberg states at different magnetic fields, and we find much more sensitivity of this Rydberg atoms, which are still in a lower principal quantum number like 35, and still we see much more sensitivity of this Rydberg states in response to the magnetic fields as compared to the ground state atoms. So here it's still ongoing, and we are in the process of doing a theoretical modeling using the optical block equations to quantify our results. So these are probe and the coupling beam in different polarization configurations to address the different ZMan states. Okay. So another project experiment which we are about to start is to do quantum sensing using microwave interferometry with Rydberg atoms. Actually, this is a theoretical prediction from someone in IIT Guwahati, you know very well, Kanhaiya Pandey. He did this theoretical prediction of microwave interferometry using Rydberg atoms, which was very interesting. And so we are going to have this experiment in our setup, where we are going to apply microwave field in addressing these various levels to do a microwave interferometry to have very, very high sensitivity of this Rydberg states to electric field. And so as I had mentioned that the polarizability of Rydberg states, Rydberg atoms is very high, going as 10 to the power 7. So it's extremely sensitive to small DC or electric fields, which makes it very interesting for quantum sensing. And for example, if you want, it can sense very accurately frequencies in a wide range, for example, terahertz or microwave or RF. And for example, if you want to measure very small magnitude of these fields, you need a probe which has to be calibrated. Now the accuracy depends on the calibration of the probe, but here the atoms are the best. It doesn't need any calibration and hence give a very accurate measurement of very small magnitude of these microwave or terahertz or RF fields.
The power of n is changing because of what?
So it's not power. I mean, it's the state. It's the Rydberg state. Yeah. Yeah. No. It's just the notation.
1 and 3 are nearly degenerate or what? 1 and 3 user ASET.
One.
No, 3 and 5. What is that?
Slight difference in the frequency. It's not completely degenerate. There's small difference in the frequencies. So we have identified the relevant states in our setup already. So, and we have also procured all the microwave sources to actually do this experiment.
Tiny electric field, nanovolt. What could be the order of magnitude of the shift?
Yeah, so the shifts will be very well within our signal to noise ratio. So what we calculated that we should be able to. So it.
You are proving actually a mixed
Yeah. So what will. So we will be, it will of course depend on the principal quantum number we are taking. So the higher the principal quantum number, larger will be the shift. So we are trying to have the experiment as high principal quantum number as possible so that we can have a very highly sensitive measurement of this microwave fields. So then I come to how much time do I have? So next I come to the measurement of correlation function, which is another very interesting measurement which gives, which tells the hidden periodicity or correlation in a atomic ensemble. So here, so here we are using the D2 transition. Yes. So correlation function, it characterizes the coherence and statistical properties of an electromagnetic field. So the first order correlation function, which is we are all familiar with, it's a degree of coherence between two electric fields. So it's the amplitude correlation such as interferometric measurements. The second order correlation function, on the other hand, gives the statistical character of the intensity fluctuation, which is the intensity correlation, just given by this expression. So it, for different kinds of sources, it can give interesting behavior like bunching or a constant state or anti-bunching for a Fock state. So this is our setup for the measurement of the second order correlation function. So we have the cold atoms and we have a very high numerical aperture lens which is inside the vacuum chamber, which is collecting the fluorescence with high efficiency. And then we have two complementary detection systems. One is the EMCCD camera and another is a APD based detection system where we collect the fluorescence in a fiber couple with a fiber coupling, and then we use a fiber splitter to split it into two take it to two single photon detector module based on APD, and then we have what is called a home built avalanche photodiode optical data acquisition system where we make the measurement of the second order correlation function. So this is the experimental setup for measurement of the correlation function. So yeah. So we are measuring this photons in the two APD and then we are, yes. Yes, they are taking the coincidence count. So here, this is the setup for our cold atoms. So here you can see the vacuum chamber where we have the cold atoms. And there itself, we have this high numerical aperture lens inside, very close to the cold atoms. And here is the measurement of second order correlation in just cold atoms without Rydberg excitations. So here, sorry?
There is nothing non-classical about that, right?
Yeah, I mean, here it shows Rabi oscillation, so which is generally if you take the fluorescence in a detector, you won't see this periodicity, but only in the correlation measurement you see at least, because at least one cycle of Rabi oscillation till the, because of the spontaneous decay, then it turns to a kind of exponential decay. This is the setup, schematic of the setup for Rydberg excitation in cold atoms. So here we have the cold atoms and the lens which is very close to the high numerical aperture lens, close to the cold atoms. And we have the 480 nanometer laser for the Rydberg excitation, which is aligned through the cold atoms. And similar to the earlier system, we have the signal, the fluorescence signal in a fiber coupler, and which is taken to the APD. So here, last month, we got the first excitation of cold atoms to the Rydberg state, which is the first time in our country where cold Rydberg atoms have been observed. And here is the signal of the Rydberg excitation to the Rydberg states of cold atoms. No, it's higher. So yeah, it's around 10⁻⁹ atoms per centimeter. Yeah.
So when you shine the Rydberg laser or something, you lose the atoms in the track, right?
Yeah, so that is the whole measurement. So this one is the fluorescence without the Rydberg excitation. So here what we are doing is we are tuning the Rydberg laser to the resonant frequency of the Rydberg state, and then we are seeing the loss of atoms. So as we are taking it out of the Rydberg state, we are seeing again the increase in the fluorescence.
The second peak is because of what?
Yeah, so that's a very good question. So here what happens is that in the MOT, so we are using the MOT light as the probe beam. We are not using an extra probe beam, which is detuned. Now, you can have two kinds of excitation. One is on resonance excitation, which is like both of them on resonant. And then there could be another two photon excitation, which are more coherent because they're off resonant. So when you have the probe beam slightly detuned, the coupling beam also is detuned to compensate for that.
So it's like again a palm probe type.
Yeah, exactly. Yes, yes.
And they are co-propagating.
So here actually.
So there is a counter-propagating. That is the reason that you.
Yeah.
There is a counter-propagating. So they are addressing different velocity classes.
Exactly. So because in probe beams, which is the MOT light is from all directions. So here we are making a correlation measurement of the atoms in the Rydberg state, which is still in progress, to look at the role of long-range dipole-dipole interaction in cold Rydberg atoms, which has much higher densities and much more controllable. So here it's the first signal of the correlation measurement in cold Rydberg atoms. It's still at 35 S-half. So we want to make a correlation measurement of the D Rydberg states, and as well as go to very, very high principal quantum number and try to see if we can see.
Can you recognize the Rabi frequency?
No, here because we are scanning, I mean, this is in the Rydberg state, which has a very large coherence time, large lifetime. So it's not the same as, very short lifetime of the earlier, ground state atoms, which is like 28 nanosecond. So that's why we, yeah. Yes, we are planning to do that. Actually, when Professor Bimalendu had come to our lab, he had also suggested the same, and we are exactly preparing to do the Fourier spectrum. So before that, we are now going to lock this two probe and the control coupling laser to a very high, Fabry-Perot cavity to have a very long-term stability so that we can do a coherent excitation to the Rydberg state, and it can be stable for a long hours so that we can take the measurement for a very long time, and then we can see, this Rabi oscillations for the Rydberg excited states. So the next step in our experiment, which is already a lot of progress has happened, is to do a single atom trapping for Rydberg excitation. So we, as I had mentioned, we have two high numerical aperture lens very close to the cold atom. So this is done so that we can focus, so we can have an optical tweezer which has a very, very small focal spot of the order of 1 micron. So that we can trap a single Rydberg, single atom in the focal spot of the optical tweezer. So why do we need such a small focal spot is that if we have such a small trapping volume, if there are more than one atom, so both of them will undergo inelastic collisions and both of them will go out of the trap. So this is what is called a collisional blockade. So this ensures, this small trapping volume ensures that there is either 0 or 1 atom in the optical tweezer. Yeah. So we have actually the dipole trapping laser and is all ready to actually make the optical tweezer. 0.55. Yeah, so we have calculated that it also depends on the size of the beam and the distance of the lens from the, so we have calculated it should give, around that 0.8 or 1 micron.
You have to have the input beam quite big.
Yeah, we are actually planning to have quite big just filling. So that is the challenge of of this experiment. But according to our calculation, this is what is it's designed to do. Yeah.
Initially, you trap the ground state atom.
Yeah.
Then you excite to Rydberg state.
Yes.
So the same trap will trap both the states.
So in the Rydberg state, it will be trapped because depending on the on the trap depth, because typically in this kind of traps, the trap depth is very high, like order of few millikelvins, as compared to other traps which are like few hundred microkelvin. But in millikelvin, we can have the Rydberg atom trapped in the trap.
It is only the dipole.
Yeah, it's the dipole force.
Actually, also the polarizability is also high.
Yeah, the for the Rydberg state.
Very high.
Depending on
Power 7, no?
yeah, n to the power 7. So this is our schematic of our experimental setup, where we have we'll have the 850 nanometer dipole trap beam to create the optical tweezer, and the 780 nanometer light, which will be the fluorescence light from the single atom, is here. Will be collected using this lens inside the vacuum chamber, and it will be directed to two complementary detection system, a CCD camera and the single photon detector module to look at the signal from the atoms. So why is single atom trapping so interesting? The ability to trap individual atoms allows controlled engineering of the quantum state, and single quantum system is necessary to encode and process information at the quantum level. Yeah, to explore quantum physics of particles at the microscopic level. So the importance of trapping a single quantum system had been recognized in 2012 with the Nobel Prize in Physics, where Serge Haroche and David Wineland had been awarded the Nobel Prize jointly for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So the idea is that the atoms will be trapped in, the single atom will be trapped in the focal spot of the optical tweezer, which will be, so we will be building up this structured light potential using a digital mirror device or a spatial light modulator. So the exact mechanism will be discussed tomorrow in Saptarish's talk, so I will not go into the details of that. So then the atoms will be excited to the Rydberg state, so that to enable the interaction between them for realizing quantum entanglement via Rydberg blockade.
So this array you
Yeah, that's what the plan is, to use digital mirror device or spatial light modulator to create this 1D or 2D array of Rydberg atoms. So why it's so interesting to have an array of Rydberg atoms in a structured light potential? So we all know that in microscopic level, it's mostly dominated by single particle physics. And of course, in macroscopic system, it's the many body physics which comes into play. But what happens in the mesoscopic regime? Is it still quantum, or when does the transition from the classical to quantum, from the quantum to classical behavior happens? So this mesoscopic regime is very interesting to probe. So the idea is to assemble atom by atom the single atoms in the optical tweezer, and then go from the microscopic to the mesoscopic regime and see, and finally using structured light potential have a large 2D or a 1D array of Rydberg atoms using a structured light potential, and look at the mesoscopic regime where this transition happens from the microscopic to the macroscopic behavior, and whether we want to explore whether we can have a scalability of such a system. Also, we can explore quantum many-body physics with Rydberg atoms. For example, Rydberg atoms can be trapped in a square or a triangular array of optical tweezers, and then we can look at anti-ferromagnetic ordering in such systems, and we can explore quantum magnetism in such a structured light potential. Yeah.
Just a query. How large you can make this grid? What is n cross n? What is the largest state you can make?
So it depends on actually, so we have this cloud of cold atoms, and that when overlapping with the optical tweezers, then array of optical tweezer will be catching the, so
4 cross 4, 10 cross 10, 20 cross 20.
in principle, at the moment 20 cross 20. That's what I have calculated with our experimental parameters. But if we go to higher and higher Rydberg level, then we can even go to more, because the blockade radius will increase. So we can go to even larger array. So that is the whole point of going atom by atom and see how far we can go in building this.
The other question is regarding the how much you can manipulate your array by this. You have to manipulate the tweezers, right?
Exactly.
So how long can you control the lattice?
Yes. So that is the
Parameter?
Yeah, so that is the advantage of having this optical tweezer array instead of optical lattices. Generally, optical lattices have like a few hundred nanometer separation, which is very hard to manipulate. But optical tweezer, we can have a few micrometer difference, and then it's easily addressable. Each of this optical tweezer, and also we can control the distance between the optical tweezers, and if we can have the Rydberg atoms to very highly excited state, the other atoms, several of these tweezers will be in the blockade radius of one Rydberg atom. So we can have quantum entanglement in a large array of Rydberg atoms. So as I had mentioned, Rydberg atoms are very sensitive to extremely small DC or electric fields. So this makes it a very highly desirable candidate for quantum sensing because of this high degree of polarizability going as n to the power 7. And hence we can use Rydberg atoms for quantum sensing and metrology. And eventually we can hope to beat the standard quantum limit via quantum tricks such as squeeze states and reach the Heisenberg limit, which is the holy grail of precision measurements. So I come to the end of my talk. So the summary is we have excited Rydberg atoms to very highly excited Rydberg states, which has very exotic properties with like large dipole-dipole interaction, large polarizability, and very long lifetimes. And these exotic properties makes it very interesting for quantum information processing, precision electrometry, and also single photon sources for quantum communication. I've described our precise transition frequency measurements for highly excited Rydberg states, and also I described our first observation of Rydberg excitation in cold atoms. and also the measurement of G2 correlation function in the presence of Rydberg excitation. And also I've discussed the future direction of atom traps in a 1D or 2D array of structured light potential for realization of quantum entanglement as well as quantum simulation and quantum sensing with Rydberg atoms. Thanks for your kind attention.
Okay, I guess we really thank Sanjukta again and congratulate her for having the first cold Rydberg atoms in the country. Well done again.